Section 4.2 is all about inverses, so inverses of relations and functions. On our warm-up, let's start with talking about does the graph or does the function f of x equals 1/2 times 2 to the x model growth or decay. I'm going to start us off by graphing in a second. So if we were to make a table out of this, plugging in some x values, getting some y values out of it, I'm going to choose -2, -1, 0, 1, 2, and we even go 3 and 4 just to kind of show what this looks like. Plugging in -2, you'd end up with 1/2 times 2 to the -2. After you go through the process of raising 2 to the -2, you'd have 1/2 times 1/4, which would give us 1/8. So really small. Similarly, if you were to plug in -1, you'd end up with 1/4. Plugging in 0, so you'd have 1/2 times 2 to the 0, so 1/2 times 1, you'd end up with just 1/2. Plugging in 1, in this case, you'd end up with 1. Plugging in 2, 2. Plugging in 3, you'd end up with 4. And plugging in 4, you'd end up with 8. Graphing these, -2, 1/2, you might, on this graph right now, it's kind of hard to see the x-axis, so let me darken it a little bit. So, actually, let me make it a thicker line. This is a little easier to see. There's the x-axis, there's the y-axis. Okay, so with that in mind, we're going to plot these points. -2, 1/8 is pretty low, so I'm going to go really close to the x-axis. -1, 1/4 is a little bit higher. 0, 1/2, 1, 1, 2, 2, 3, 4, and 4, 8. 8 would be 5, 6, 7, 8. Okay, right there. And if we were to connect these on that left side, just like we talked about in the 4.1 notes, try to make it so that it gets really, really close to the x-axis, but it doesn't quite touch. Folks, as it's going up and to the right, that is a demonstration of exponential growth. So just a quick refresher from what we did in 4.1. Our goals for this lesson, our goals for the day, are to graph and recognize inverse functions inverses of relations and functions, and also we're going to find the inverses of functions. For this first example here, let's plot these first points. Let's call this first function f of x. And let's plot those points 0, 2, so we got a point there. 1, 5 is up here. 5, 6, that is over here. And 8, 9 is going to be up here. I'm also going to connect these dots, even though it doesn't officially say we need to. It might help a little bit with our visual. For the inverse, I'm going to do that in blue. So our inverse down here. As I said in the previous slide, we're just going to literally swap the x and the y. So 0, 2 is going to become 2, 0. 1, 5 is going to become 5, 1. 5, 6 is going to become 6, 5. And 8, 9 is going to become 9, 8. So let's plot those. So we got 2, 0, 5, 1, 6, 5, and 9, 8, which should be right there. So if we connect these dots, you can kind of start to see how these are inverses of each other. Again, one of the definitions, or part of the definition we talked about in the previous page, was that the points are reflected over the line y equals x. So here is the line y equals x. You can see it kind of acts like a mirror to go from the red graph to the blue graph, and vice versa. You can reflect from the blue graph back to the red graph. Now, let's talk about notation a little bit. So when the relation is also a function, so if the f of x is a function and its inverse is also a function, we use the notation f inverse of x, and that is what this notation is right here. So the inverse is read as, or it looks a little something like this. And again, we read that as f inverse of x. Now remember, inverses kind of undo the other function. So, for example, if you were to take an input 3 and plug it into the function x plus 6, you get an output of 9. The inverse function will undo that. We take that output and plug it into the other function, it gets back to where we started. An analogy I often use is something that's a little antiquated. It also uses an imaginary machine. That's going to seem a little weird, but let's talk about that. So what I usually talk about is a change machine. So thinking about like if you go to an arcade, which isn't much of a thing anymore, or if you go to like the laundromat, you can put a dollar bill in and the change machine will give you 4 quarters back. Now, the inverse is this hypothetical, mythical, unchanged machine where you put 4 quarters in and you get your dollar back. They undo each other. So the example that we have here, the input of 3 into one function, you get an output of 9. You take that 9, plug it into the other function, you get an output back of 3. So in order to figure out how to make a function, we're going to have to come up with a way of solving. So again, we're going to simply swap the x and the y just like we did in the previous part in our coordinates. So if we've got f of x equals 3x plus 8, essentially that's like it's as if it were y equals 3x plus 8. We're going to start by swapping the x and the y. So I'm just going to rewrite this, y equals 3x plus 8, and then the inverse is going to be x equals 3y plus 8. Now, because we want it to be something that we can kind of like graph and show it on our calculator or show it on a graph, we're going to start solving this for y. I'm going to subtract 8 from both sides, and we end up with x equals, I'm just going to move it over here. We have x minus 8 equals 3y. To get y all by itself, we're going to divide both sides by 3, and we end up with x minus 8 over 3 equals y. Now, proper notation on this one, we're going to say f inverse of x equals x minus 8 over 3. Or if you want to put it in a more familiar format, sorry, let me just move my image here. If you want to put it in a more familiar format, this is technically a linear graph. Not technically, it is a linear graph. So if you wanted to, you could say f inverse of x equals x over 3 minus 8 over 3. So it gives us a slope of a third and a y-intercept of 8 over 3. Sorry, negative 8 over 3. Let's try this out for a couple more examples. So on example 2, I've got 3 examples here. For non-honors algebra 2, your format's going to be a little different in the order, but it's the exact same problem. So just make sure you're hunting and finding out which problems are which. So again, I'm going to start off by rewriting this function as y equals. So we got y equals x minus a half. The inverse would just be x equals y minus a half. So again, we literally just swapped the locations of the x and the y. Now to solve for y, we're going to add 1/2 to both sides. And we end up with x plus a half equals y. That is our inverse. And so we're going to say in proper notation, f inverse of x equals x plus 1/2. Similarly on the next one, if you want to try this one on your own, you can pause the video. But I'm going to start by rewriting it as y equals 3x. And again, the inverse, we just swap the x and the y. So we have x equals 3y. This one's going to be pretty quick and easy to solve for y. We're going to divide both sides by 3. We end up with x over 3 equals y, or putting it in our inverse notation, f inverse of x equals x over 3. Or if you want to, you could say 1/3 x, thinking about the slope of a linear equation. Last one's going to require a little bit more work, but it's the same process. So again, start off by writing it as y equals 3 times x minus 7. The inverse, sorry, I scrolled too far. The inverse is going to be x equals 3 times y minus 7. Now to start this one off, we're going to kind of do PEMDAS or PEMDAS in the reverse order. So we got to do that multiplication, get rid of that first before we do the grouping. So I'm going to divide both sides by 3. So that means we end up with x over 3 on the left side equals y minus 7. Again, to solve for y, we're going to add 7 to both sides, and we end up with x over 3 plus 7 equals y. Again, putting it in proper inverse notation, we're going to say, I'm just going to move this over here, f inverse of x equals x over 3 plus 7. And if you want to put it in, again, slope-intercept form, we got f of inverse of x equals 1/3 times x, then plus 7. So either of these answers is perfectly acceptable.